Imagine an app that is only allowed to go offline for like 5.5 minutes.
Right, and not per week.
Yeah, exactly. Per year. I mean, that is the reality for the invisible financial engine, allowing you to just, tap your phone and pay for your coffee.
Because usually a standard web app, like maybe a local restaurant's ordering site, it handles maybe 100 to 1,000 transactions per second.
Right. So today's deep dive is about global payment rails. We're looking at how these mega systems pull off 10,000 plus transactions per second flawlessly without regional outages or database lockups.
It is a completely different tier of engineering. When you scale up to that level, I mean, the physics of computing actually change. You can't just buy a bigger server.
Right. Let's look at raw volume first. Think of a concert ticket flash sale.
Oh, a classic nightmare scenario.
Exactly. 10.00 AM hits, and 50,000 fans just click buy in the exact same second. A standard relational database, physically trying to write all those requests to a disk sequentially, well, it would just lock up.
Yeah, you'd get this massive request queue.
Right, and like 80% of buyers would just hit a 504 gateway timeout.
Because the database is a massive bottleneck. To survive that stampede, these systems shift to horizontal scaling.
Okay, meaning what exactly?
They use global Anycast load balancers to, cache those simultaneous requests and distribute them across hundreds of containerized worker nodes.
So instead of one massive funnel, Anycast routes you to the nearest least busy node.
Exactly.
But wait, you still have to write the data somewhere without creating a new bottleneck, right?
Right. So instead of forcing a database to write down every transaction the exact millisecond it happens, they drop the request into a massively parallel inbox.
Like Apache Kafka.
Yes, Kafka is a great example. It acts as a shock absorber. It catches, something like 500,000 messages a second.
Wow.
Yeah, and it holds them safely until the database workers can process them at their own pace. And for reading data, those workers just check in-memory Redis clusters in less than 1 millisecond.
Well, catching the volume is great, but network lag is kind of the silent killer here.
Oh, absolutely.
I'm thinking of like a subway turnstile during morning rush hour. If you have to send a fraud check and a ledger validation all the way across the country, it might take 800 milliseconds.
Which is an eternity.
Right. Commuters would physically crash into the gate.
Yeah, geography is the main enemy of sub 100 millisecond latency. The data physically has to travel, so they use edge data centers.
Oh, okay.
They place the processing node in the same city as the turnstile, which drops network transit time down to about 5 milliseconds.
So it's like hiring a local bouncer for the club instead of calling the police chief in another state every time you need to check an ID.
Perfectly said. The decision happens right at the door.
Makes sense.
But even at the edge, they can't afford to run sequential checks. They use asynchronous non-blocking I/O to run fraud scoring and balance checks concurrently in parallel threads.
Okay.
And rather than placing a heavy lock on your account in a traditional database, they use optimistic locking to update the math in ultra-fast RAM first.
Wait, doing the math in memory sounds incredibly fast, but isn't RAM volatile?
It is, yeah.
So if that edge server loses power before saving the receipt to a hard drive, doesn't the money just, vanish?
It would if they didn't decouple the logging. The system assumes the transaction is valid, updates the RAM to get you through the gate in 42 milliseconds.
Wait, really? 42 milliseconds?
Yeah, it's lightning fast. But it instantly copies that state to a distributed persistent log we mentioned earlier. The heavy database audit just happens asynchronously in the background.
Okay, but speaking of servers losing power, what happens in a physical worst-case scenario?
Like what?
Let's say a backhoe cuts a fiber optic cable and a power transformer explodes in a primary data center on a Tuesday afternoon. How do you maintain that strict 5 nines uptime?
Well, through multi-region active deployment.
Okay.
These payment services live simultaneously across geographically isolated data centers like, US East, US West, and Europe.
Got it.
If that transformer explodes in US East, global load balancers instantly redirect 100% of the traffic to the other regions in under 500 milliseconds.
But hold on. If you're suddenly routing millions of overlapping transactions across regions that fast, how do you prevent double spending?
It's tricky.
I mean, if US East goes dark, how does US West know I just bought a coffee a millisecond ago?
Because of continuous state replication and eventual consistency. However, under sudden immense load, keeping every single database perfectly synced across the country is just impossible.
So what happens?
That is where circuit breakers come into play. It's a design pattern for graceful degradation.
Meaning it strategically shuts things down to survive.
Exactly. If syncing loyalty rewards points or generating a digital receipt starts failing and threatening the main system during that failover, the circuit breaker trips.
Oh, wow.
Yeah, it disables those non-essential features instantly. It sacrifices the peripherals to keep the core card authorization 100% operational.
So it sacrifices the fluff to save the transaction.
Pretty much, yeah.
That is why your digital financial life actually works. When money is on the line, standard architecture just doesn't cut it.
No, it really does.
The difference between the acceptable 9 hours of downtime for a normal app and the 5 minutes permitted here requires a completely different mindset.
Absolutely.
So next time you tap your card and it takes like 2 full seconds, instead of being instantaneous, ask yourself what massive physical infrastructure just exploded in the background, forcing the system to gracefully degrade just to approve your coffee.